In Chapter 8, we're going to look at some additional topics in trigonometry, starting with Section 8.1, which is the law of sines. Up to this point, we have worked exclusively with right triangles. The trigonometric functions, identities, and formulas, including the Pythagorean theorem, apply specifically to right triangles. We will now consider oblique triangles, which are triangles that do not contain a right angle. The figure below shows some examples of oblique triangles. An oblique triangle has either three acute angles, meaning three angles, all of whose measure is less than 90, or it can have one obtuse angle and two acute angles, like the second triangle. The law of sines says the following. So typically in this section, we'll denote the angles using capital letters A, B, and C, and the corresponding sides that are across from those angles will be denoted by lowercase letters A, B, and C. For example, if I focus on this very first triangle, this particular angle is denoted as angle A, and the side across from it we will denote with lowercase a. Similarly, if this is angle B, the side across from it will be lowercase b, and if this is angle C, then the side across from that angle will be side little c. The law of sines says that if you take the ratio of the length of a side and divide it by the sine of its angle, that this ratio is consistent throughout the entire triangle. That is, little a divided by the sine of angle A is equal to side B divided by the sine of angle B, which is equal to side C divided by the angle of sine C. So this is our brand new law of sines. And what's nice about this law of sines, and the thing you should keep in mind as we're working throughout this section, this law of sines applies to any triangle, not just right triangle, but this applies to obtuse triangles, oblique triangles, etc. Something that we did earlier in the class when we defined the basic six trig functions is we worked on solving triangles, and we're going to now pick that up by solving some non-right triangles. In example 1, they say solve the triangle below. We know that means to find the measure of all of the sides and also all of the angles. So our goal in this problem is we want to find the length of side A, side B, side C. We also want to find the measure of angle A, angle B, and angle C. Let's start off by writing down the things that we do know. We know that based upon the diagram that angle C is 63 degrees, angle A is 46 degrees, and we also know that side C is 56 inches. Of these, the next easiest thing to get would be angle B. We know that in a triangle, the three angles have to add up to 180. Because we know A and C, that's going to be 46 plus B plus C is 63. This should equal out to 180. That is that B plus, if I combine those, 46 plus 63 is going to be 109. It would be equal to 180. And then subtract 109 from both sides. We would get that the measure of angle B is going to be 71 degrees. So we now know that B is 71 degrees. And now we're going to solve for either side A or side B next. Let's actually solve for side A. In order to solve for side A is right here. I know the angle across from A. I know angle A is 46. And then to set up a law of sine problems, essentially what you're looking for is a situation where you have a known angle and its known side. And in this case, that's going to be side C and angle C. I know that angle C is 63 degrees, and I know that side C is 56. So if I want to solve for side A, I can set up a law of sines ratio between the pairs of sides and angles for A and C. The law of sines tells us that side A divided by the sine of its angle, A, is equal to side C divided by the sine of angle C. We don't know A, we're trying to solve for it. I have the sine of 46 degrees would be equal to, C is 56, divided by the sine of angle C, which is 63 degrees. This gives us an equation where we can now go ahead and solve for side A. All I would need to do is multiply both sides by the sine of 46 degrees. These would then cancel, and so what we would find is that A will be equal to 56 times the sine of 46 degrees divided by the sine of 63 degrees. And for this value, let's round it to 2 decimal places. When you go to enter this calculation into your calculator, it's very important that you want to make sure that your calculator is set to degree mode. For the majority of the class, we've been working within radians, but this is the one time where you definitely want to make sure you're working in degree mode. If we take 56 times the sine of 46 and divide it by the sine of 63 degrees, that should give us a value of about 45.21. So side A is 45.21 inches. We can now go ahead and solve for side B. Just make a little bit of room. When I solve for side B, we can do the same thing by setting up a law of sines ratio. Side B divided by the sine of angle B is going to be equal to, and now at this point you actually have a little bit of choice. We now know side A and angle A, and we were previously given side C and angle C. So you could set B over sine B either equal to A over sine A or C over sine C. However, one of the things we discussed earlier in the class is if you look at the value we have for A, that was a value that was rounded, it's not exact. So if I try to use that rounded or previous answer in a following problem, that might compound my rounding error a little bit. So always try to go back to the original information in the problem. I'm going to stick with using side C and the sine of angle C. So side B divided by the sine of its angle. Angle B was 71 degrees. This should be equal to side C, which is 56, divided by the sine of angle C, which is 63 degrees. You would go ahead and solve for B the same way. Multiply both sides by sine 71 degrees, and we would find that the exact value of B is 56 times the sine of 71 degrees divided by the sine of 63 degrees. We can go ahead and enter that into the calculator. And what we should find is that B is going to be approximately 59.43 inches. And now we have finished the problem because we've solved for the length of each side and the measure of each angle.